Welcome back. I'm going to take a look at inverses once again, and today what we're going to start with is a little bit of a graphical study on inverses. And the first question here is asking us whether or not this graph is a function. And the easiest way for me to determine if it is a function or not is to draw a vertical line. By drawing the vertical line, let me zoom in on this for a moment, you'll notice that the graph itself passes through that vertical line exactly once. Regardless of where I draw my vertical lines, it will always follow this pattern. Therefore, the answer to this is yes. And the reason for that is that it passes the vertical line test. But the technical reason for that, obviously, is that for every value of x, there's exactly one value of y. That's what the vertical line test will help us determine. The horizontal line test is used to determine if the inverse of a graph is a function. So using our previous problem as an example, if I wanted to know whether or not the inverse of this graph would be a function, I would simply draw a horizontal line. Notice that through that horizontal line, 3 values touch on the graph. That means it will not pass the horizontal line test. So let's go ahead and take a look at a few more examples to see if the following graphs have an inverse. That's the key to the horizontal line test, is determining if the inverse is a function. So the answer to question number 1 will be no. I'll draw myself a horizontal line through this absolute value function. Notice that it passes through twice. Number 2, or graph number 2, draw a horizontal line here. Notice that this passes through once. If I were to move it anywhere along this graph, the same would be true throughout. Now that, we would learn in another way, is also true because this is a transformed version of the exponential parent function. The inverse of an exponential parent function is the logarithmic parent function, and the logarithmic parent function obviously is a function. Our third one, parabola laying on its side. So if I turn that back on its head again, you will notice that it will pass the horizontal line test, and since it's a parabola, is a function. If a graph is known to be one-to-one, that is when it passes both the vertical and horizontal line tests, making the graph and its inverse a function. We're going to take a look at a few more graphs here to determine or explore one-to-one relationships. We begin with the vertical line test. You'll notice it touches it once. Likewise, that would be true at any point. And I'm going to go ahead and go through the horizontal line test here. Notice that it passes through here and here in this particular place, so the answer to one-to-one relationship is no. In this particular case, we're going to address the vertical line test first, even though the answer to that is obvious. There it passes. The only place where we're going to have issue with the horizontal line test is going to be right here along the x-axis. So if you look carefully and understand the behavior of rational functions, especially around asymptotes, you'll notice that this graph will approach from above but never touch the x-axis. This part of the graph will approach from below and never touch the x-axis. Therefore, this one has a one-to-one relationship. The vertical line test in graph number 3 is easily passed, but the horizontal line test clearly fails. Therefore, the one-to-one relationship for graph number 3 is no. All right, moving on. What we're going to do now is we are going to determine and explore and practice solving inverses algebraically. And we're going to start by switching x and y. And then we're going to solve for y. Now the difference between yesterday's notes and today's notes, as you begin to see scanning through these problems, is that some of these have restrictions. Now that plays a very important role when we solve both a graph and its inverse. If one of the functions or one of the equations has a restriction, the inverse has to follow that same restriction as well. Okay? We'll take a look at that in a couple of examples. So the first one, not so difficult. We switch to y. Then we switch the position of x and y. And now we solve for y. Question number 7. Now in this case, we're going to go ahead and look at the original function before we begin. The original function has a restriction. The restriction is that it cannot be below 0. But what I like to do instead is I like to take a look at the sketch of the graph. This is a square root parent function, so it looks like this. Okay? The inverse of this function must also look exactly like this. Now let's go ahead and solve. Okay. Putting this particular graph on here, it looks like this. These two graphs are not identical. In fact, what is missing from the original that the inverse has is this negative branch of the parabola. Now, because the original has a restriction, the inverse must also carry that same restriction with it. So in order to solve this problem and answer it correctly, you must properly identify the restriction. The restriction in this case is that x must be greater than or equal to 0. Graphing both the function and its inverse with the restriction will show that now you have two identical graphs. Without the negative branch of the parabola, you'll notice that I have a square root function which has been flipped over the line y equals x. Question number 8 looks very similar to question number 7, so we'll be solving that one in the same way. Multiplying both sides by 3, and then taking the square root of both sides gives me okay, when you square root both sides of an equation, you will always get two solutions, the positive and the negative. So we want to take a look at both of these for a moment and look at what's going on. If the restriction x greater than or equal to 0 was not on the original function would look like this. But because of the restriction, this branch is missing. That means that in this particular problem, the plus and minus is unnecessary because the plus and minus means that I would draw two branches of the inverse as well. But with the original being restricted, the inverse must also be restricted as well, which means that the correct solution to this problem is the square root of 3x only. All right, question number 9. Be moving the 5 first by using subtraction. X minus 5 equals the square root of y plus 2. Squaring both sides gives me x minus 5 quantity squared equals y plus 2. Finally, subtracting both sides by 2. Remember, the 2 stays outside because the exponent locks the quantity x minus 5 inside the parentheses. And now I have this. The original function is a square root function. Due to the transformations, it moves left 2 and up 5. The inverse of the function is a parabola. The parabola, due to the transformations, moves right 5 and down 2. Without any restriction, you'll notice that both of these graphs are different. Therefore, I must restrict the inverse of the function because the original had a restriction. If I erase the negative branch of the parabola, you now have an identical graph and its inverse graphed properly. Therefore, I must restrict the parabola at its vertex, which is x equals 5. So I'm going to go ahead and rewrite this problem as x minus 5 squared minus 2 equals f negative 1 of x when x is greater than or equal to 5. We're going to take a look at these functions in more depth and how they actually work with the Desmos program tomorrow, so you can see that more clearly. And there you'll understand why our restrictions are in place a little bit better. So please ask questions that you may have. At this point, however, I want to give you some time to work on question number 10 and 11. Mostly, I'd like you to practice solving inverses of these complicated problems, okay? But tomorrow we're going to go ahead and look at these two with their restrictions as well. So go ahead and have those ready for the beginning of class. The last question that I want to address is question number 12. This one can be a little bit tricky. So I thought very carefully about how I wanted to word this one so it was not confusing, okay? So if we go back to these problems prior, you'll notice that basically all we've been doing the entire time is solving for the other variable. Well, when it comes to real-life examples and inverses, that's the easiest way to explain how to actually solve for them. So, in this particular problem, when it's asking you to find the inverse of a function that represents a surface area of a sphere, all we're going to do to make this problem simple and easy to understand is actually solve the equation for r. By doing this, you will have found the inverse of the function, and therefore you can answer the question more easily. So the first thing I'm going to do is go ahead and divide both sides by 4 pi, and then I will take the square root of both sides following that. Now I'm going to see that the inverse of this function is the square root of s divided by 4 pi. Remember, when you square root, you get two answers. Because it's a real-life example, we don't need the negative one. That's why I leave that off in this particular case. Now I'm going to answer the question that it's asking. What is the radius if the surface area is 100 pi? The pi's cancel, and 100 divided by 4 is 25. The square root of 25 is 5, so the radius of my circle is 5. Please do not forget to solve questions number 10 and 11 and have those ready to share tomorrow at the beginning of class.